Good afternoon. Welcome to Bird Lecture Series, Biostatistics in Action. Today's speaker is Dr. Jeff Goldsmith, an associate professor in the Department of Biostatistics. Dr. Goldsmith's statistical research is mainly focused on functional data analysis with application to the use of motion kinematics to understand motor control, skill learning, and recovery from following stroke. Dr. Goldsmith will talk about data science and clinical research. Thank you.
Welcome, everybody. This is a small enough group that we can keep it informal. If you have any questions or anything like this, feel free to shout it out at any point. I'm happy to have the opportunity to talk today in the Bird Lecture Series about data science and clinical research. I spend a lot of time thinking about data science and teach a class in data science and try to incorporate it as much as possible into my own sort of clinical collaborations. And so it's fun for me to have a chance to sort of think about this and then talk through what exactly we mean in this context. So I'm going to, in the structure of this talk, what I'm going to do at first is try to contextualize or explain what I mean by data science, because I think it's a new enough area that there's still some confusion about what exactly this is. And then after sort of spending some time talking about sort of data science as a field, I'll go through a specific sort of method in data science, a specific statistical learning technique, which I think exemplifies what the sort of new area in statistical learning or machine learning means in general or does in general and how it might be used in clinical research. So when I say data science is pretty new, this is what I mean. This is coming from Google Trends to get an idea about what exactly has been going on over the last, let's see, this is 15 years, give or take. So since January 2004 up till about 2012, nobody really even mentioned data science. It wasn't a thing that existed, and since then it has sort of taken off roughly exponentially, and it seems to be still on the sort of upward trajectory. I don't think we've hit peak data science yet. That's still sort of a little bit down the road, but we're sort of seeing more saturation of data science in this kind of a context, right? And it's starting to penetrate beyond the sort of traditional sector of applied statistics or applied statistics in tech companies or in things like this, and into the realm of things like clinical research and biomedical data science. And so there's a challenge, I think, in defining with something that is this new, what exactly people mean by data science. And this is a quintessential sort of a starting point, the Venn diagram of the data science skill set that gives an idea about what exactly is going on. And so you see in this figure, data science is sort of the central thing that overlaps math and statistics knowledge. So you do have sort of traditional statistical techniques. There is substantive expertise. So what exactly is going on in, for example, a clinical area. And then in addition to that, hacking skills, which is sort of a broadly defined collection of whatever you like computers and you'll play around with things and hopefully that works. And like I say, at the intersection of these things, you have something called data science. And this, like I say, is one of the first things that people have tried to use to explain what data science is, what we mean by this, and what we might be looking for. And I would say from there, things got a little bit out of hand, right? So then we got a new picture that came up looking like this. What this one sort of says is at the middle of this data science cloud, you have a data scientist who is curious and creative. They know some stuff about computer science, also statistics and artificial intelligence, data management, art and design, entrepreneurship. You start getting a lot of things, and it just sort of kept going, right? So here's this one, you know, it cracks me up. You've got business sense, business strategy, domain knowledge, and then these sort of vectors of pattern recognition and AI and whatever. And like what I think this sort of exemplifies is that data science is new enough that it is poorly defined, and I think that is useful for people to keep in mind in all settings because it informs what you might expect from data science and what you might expect to see from a data scientist. And so I think this is sort of another one that I'll touch on a little bit. So you've got math and statistics over here, things like machine learning, experiment design, optimization. You get programming and database. You got to know relational algebra and Python and R and SQL. You need to have domain knowledge and soft skills, curious about data, influence without authority, meaning you have to be able to convince people to do things even though you have no real position to convince them to do that, which is, you know, that's a great skill for anybody to be able to have. And then on top of that, you've got communication and visualization, storytelling skills, visual art design, all of these different things, right? And so that, like I say, the reason that I think that this is useful, the reason that I think that this is important to understand is because it gives a sense of the data scientist as somebody who is out there and willing and able to do just about anything with any data at any time and like work magic with those things. And I think that's a difficult stereotype for any person to live up to, and that more recently has been sort of noted in things like this. So when you sort of list out this whole collection of skills and you say this is what it takes to be a data scientist, you end up with something that just does not exist. And so you have this picture of a unicorn, which, just like the data scientist on the previous slide, is a thing that doesn't actually exist in reality. I am happy to call myself a data scientist, and on a good day, I might have like a quarter of the skills on a slide like this. It's not a thing that really happens in real life, right? But it does shape what people look for and what people expect when they say, I've got this data set and I'm going to work with a data scientist and come up with something, right? So that's one reason that I think definitions of this variety are not particularly useful, is because it gives you this idea of a data scientist as somebody who is going to be out there in the world and able to work wonders with whatever data set you give to them, absent whatever domain knowledge you might have or anything like this, right? But there is, I think, in addition to that, a side of all of these definitions that is good, or at least that's informative. And I don't know if you guys know this sort of story of the blind people and the elephant, and you sort of get a bunch of blind people and they're all sort of touching the side of something big and they can't actually see it. And so if they're touching the side of this elephant, one of them calls it a wall or a rope or a fan or anything, and nobody is right about exactly what it is. No narrow definition is exactly the right thing, and you can't just stack all of these things up because then it's not right either. But what is helpful is that all of these different definitions and all of those sort of slides that I showed on the previous couple of pages, all of them are getting at some archetype, some stereotype, something that embodies the values, the sort of goals, what you might want out of a data scientist, even if none of those things is exactly perfect, right? So what I think each of those things tells you is that at best, what a data scientist is somebody who is interested and engaged in a data set, who is willing to learn whatever sort of substantive knowledge they need to be effective in that context, and then has the analytic skills to be able to translate the goals, the insights into actual models and to derive knowledge from that, right? So I think, it's easy to look at a figure like this and sort of poke fun at it, and I think that's probably the best thing to do with something like this. But there is also a lot of truth in here, meaning that it is important to have some programming skills, to know some math and statistics, to be able to engage with researchers and understand the problems that they have, and then to be able to communicate effectively. And I think all of that is fair, even if that it's not necessary to know MapReduce concepts and Hadoop and be a hacker mindset kind of person, right? All right. So then this, I always like this cartoon as well because it also sort of emphasizes that same kind of a point and illustrates the limitations of a data scientist depending on how you might define what a data scientist does and is, right? So the emphasis on context and the emphasis on understanding a setting is hugely important because one of these sort of things that has been a theme throughout each of these different slides is the emphasis of something that you can sort of refer to as algorithms or machine learning or whatever, but basically like you give somebody a data set and failing any other input, they will have on their toolbox some shelf, some algorithm that they can throw at that data set and it's going to solve whatever complex problem exists in a domain. And the truth is that that's just never how it works out in practice, right? That somebody showing up with just some tool set, with just some advanced neural networks or things like this, that is not in and of itself going to solve whatever problems you have as a clinical researcher. And I think the reason that I like this is, like I say, is in some sense to temper expectations so that people know going into it what data science is, what a data scientist might be able to do realistically, and then what sort of things seem to be pie in the sky, like based on maybe a misunderstanding of the strength of some of the tools that are available, or on the abilities of a individual researcher, right? So I like this figure. I guess it's also worth, I always pause here to ask whether or not data science is a buzzword, right? If there are all these caveats to all the things that are going on and it's sort of taken off in the last couple of years, it's worth asking maybe, is data science just something that is like a made-up term for something that doesn't really exist in the world? And I don't think that that's the case, right? I think personally, like I say, I teach a data science course, and I would consider myself to be a data scientist. And so I think there are things that exist inside of this definition and inside of this domain that are real and not sort of specific to a buzzword. I mean, that said, data science has all the hallmarks of a buzzword. It's loosely defined. It's grown exponentially in the space of a couple of years. And there's a lot of things that could fall under this overall umbrella. But I do think that the popularity of this term sort of speaks to some desire out there in the community for people who are interested and engaged and have more than sort of the traditional statistical approaches in their toolbox, right? All right. So as a first idea of one of the things that seems to be important in the context of data science, and this is not a method per se, it's more of a theme that exists in data science work, and this is a theme of reproducibility, and we'll hopefully have a chance to tie this to broader discussions in science and especially in clinical research specifically, but a very specific thing that many data scientists are worried about is reproducibility. And what I mean by reproducibility is the following. This is a particularly narrow definition, but given the same data and the same code, anybody should be able to reproduce the same results. Now, this is way short of saying that given the same data set and no code, you should be able to reproduce the same results, or given the same hypothesis, you should be able to produce the same conclusions. All of that, I would say, falls under the context of replicability, which I'll talk about in just a minute. But reproducibility is a very narrow definition, which means I should, as a researcher, be able to take whatever code I have written right now, or whatever code I have written 6 months ago, or whatever code I wrote 3 years ago, hand that off to somebody else who has some questions about it, and they should be able to obtain exactly the same things that I wrote in the first place. Now, this part of the reason that I point this out as a concrete emphasis of data science is, like I'll talk about in just a minute, this is one of the conversations that has been going on as data science has been forming, and it really influenced the direction that the field has taken. But it also sort of speaks to a lot of the characteristics, a lot of these sort of inherent values that people who gravitate towards data science have. And one of them is that openness is something that is valuable, right? Rather than sort of being a lone researcher off in the corner doing this analysis and reporting back p-values, I would like to be as transparent as possible. And I think that that actually has benefits, meaning that I'm going to make mistakes as a coder, as an analyst, as a researcher. And once I make those mistakes, I would like them to be seen by as many people as possible, as quickly as possible, so that they can point them out quickly and I can fix them. Right? And realistically, a lot of these things get solved during the research phase, before publication, before anything like this. I hand some initial results together with code to a collaborator, and they look through and they say, well, that number doesn't look right, and then we can have a conversation about that. If all we sort of are focused on is that end result of the p-value, it's very difficult to identify and fix those errors early on, and so I think that emphasis on reproducibility is helpful there. One of the other things that this emphasizes is that the code you use to do an analysis is important in the context of the research as a whole, meaning that the end result clearly is going to be a paper, is going to be something like that. But as a part of that, the code that you use to produce those analyses, the code that you use to produce those results is critical to the success of that endeavor, meaning that somebody else should be able to use that in some context or to learn from it to understand what exactly you did and why you did it that way. There are new tools to encourage reproducibility, and I'll show you an example of this in just a second, but I would not say that reproducibility is platform dependent, and I'll comment on that in just a second. So what I mean by reproducibility is the following. So this is an example. This is actually a report that I wrote, a couple of months ago, focused on some analysis. We were doing a response to a reviewer. We needed to do some propensity score modeling. And what I put together is something that includes both an overview of the document as a whole, sort of talked about what it is and why we're doing it, but also included all of the code that goes along with each of these different segments, right? So ideally, at any point in the future, if I need to go back and revisit this, or if somebody comes forward and says, I think that you did this analysis wrong, fine. I can just email them this thing and say, look through, check the code, see what you think, see if you agree or disagree or whatever. But the idea towards reproducibility is to combine the analysis and the discussion and the results all in one place that's easy to understand, right? And so we sort of put these reports together. We've got some propensity score analyses, we've got some Kaplan-Meier curves, we've got sort of all of this in one handy place, and we can go back and revisit exactly what we did at any point. Now, like I say, this is one of those things that I think is a useful tool for encouraging reproducibility, but reproducibility as a concept is not platform specific, meaning you don't have to use R or R Markdown to be reproducible or to do reproducible research. And just take some time and some care when you're putting together your SAS file or your SPSS file, whatever it is you're using, take that time to be concerned about the ability to rerun these analyses or to share that code with somebody else, and you're off to the races. You're in good shape. Good. Questions on reproducibility? Fantastic. All right. So I like to think of reproducibility as one concrete response to a broader challenge in clinical research, which is the idea of replicability, whether or not the scientific findings that we are all obtaining and reporting and publishing, are those things all sort of true in a broad scientific sense, right? And I think that this is an important thing to discuss because there's a lot of discussion about this in science in particular, especially in clinical research, but also more broadly about that. So this is something from the Scientific American. Is there a reproducibility crisis in science? And I would point out that here they're using reproducibility to mean what I would call replicability, but this same general idea. And a lot of this comes from a paper, God, I don't remember now, 2004, maybe even a little bit before that. Are people familiar with this paper, Why Most Published Research Findings Are False? Heard of this? Yeah. So there's this idea came out a while back. This author, John Ioannidis, wrote generally about the idea of if you're using sort of usual statistical tests, a usual statistical framework to do whatever analyses you're doing, there is a very high chance that you are going to end up with false positives, right? Some of your hypotheses are true, some of your hypotheses are false, and depending on what that balance is and where you set your alpha level and where you set your power, you can end up with a huge amount of false positives for a relatively small amount of true positives. And he argued, really, that that's exactly what was happening, that most of the hypotheses that people were testing were probably untrue and everything was underpowered, and so you were going to end up with all of these results that were spurious, right? And that the few true results would be masked by an overwhelming cloud of false positives. Now, I think that is an overly pessimistic view of research in general, but that was the point that he made, and it got a lot of attention, right? And so this came about, or was being hotly debated in statistics especially, about the time that data science as a field was forming. And so I think the emphasis on reproducibility and on transparency and on sort of being upfront and clear sort of got baked into data science because of this domain, because of this sort of milieu that was going on around data science as it was forming. I would point out that the reproducibility part of things is a very narrow aspect of replication, right? Replication you might sort of think of as if somebody starts with the same hypothesis and conducts the same experiment, or at least conducts an experiment to test that same hypothesis, will they come to the same conclusion, right? So there you might start with a question or a hypothesis, is this exposure good or bad for people? And then there are a lot of decisions that get made once you start with a particular question to end with a claim that yes, this is bad for you, or no, this is good for you. And those are how you formulate your specific hypothesis, how you design your experiment, who is conducting the experiments and how they gather the data, how you're going to go about doing the analysis, what the analyst actually decides, the boots on the ground, how they do things, the code they implement, and then the estimates and inference that they produce. You might add to this p-values. And then whatever claim you make at the end of this. And reproducibility focuses in very narrowly on the code part of things, which is a subset of replication in general, but is sort of geared towards this broader idea about transparency with your analysis plan and your data and how you're going about doing things, and even sort of trying to build in things like experimental design, right? So I think all of that is important in this context and sort of forms one of the backbones of data science as a discipline. Good. Okay. So I want to shift gears a little bit from like what is data science broadly and why do we care about reproducibility to what I think of as maybe a little bit more commonly understood when people think about data science. And I think what people often think when you hear the term data science are things like statistical learning or machine learning or AI or deep learning or neural nets or whatever. There's all of these other things that are out there that don't seem to fall within traditional statistical approaches, but that are getting a lot of traction. And by that I mean there's sort of articles like this, Machine Learning in the Profession of Medicine. This was a sort of opinion article in JAMA from 2016. And this one I bring this one in because I think it has this sort of view of data science or the view of these sort of statistical learning approaches as being the kinds of things that are going to solve all of the problems in the world, right? There's sort of a breathlessness to the reporting that's inside of this article, sort of a belief that everything is going to be great because now we have data science or now we have machine learning. And so you see things like previously unimaginable opportunities to apply machine learning to the care of individual patients in medical practice are currently within grasp, which is probably true. How revolutionary that's going to be sort of depends on things. They sort of follow up machine learning algorithms can accommodate different configurations of raw data, assign context weighting, calculate predictive power of every combination of variables to assess the diagnostic and prognostic elements. So the implication being whatever data you have in whatever form you have it, throw it at a machine learning algorithm and it's going to solve the problems that you have. And that sometimes can be the case, but it's relatively rare that it works out exactly like that. So I don't want to give the impression that I think there are not a lot of strengths to using machine learning approaches, but I do sort of like to tone it down at least a little bit in terms of what you can expect to get out of this. And I think there's a instructive example, or at least an instructive counterexample to all of the successes of machine learning and other kinds of ideas in the context of clinical research. This is sort of a little outside clinical research, but useful nonetheless. Are people familiar with this Google flu trends thing? Yeah, so the folks at Google wanted to detect flu outbreaks using search engine query data, right? And so I think this gives you a sense that, one, Google has a lot of data at their disposal and they've got a lot of useful things that they can do with it. And there are smart people at Google who went about trying to solve this problem. And what they found was that they were, in fact, able to predict flu trends for a number of years in a row using 2004 to 2007 search trend data and then actual CDC measured flu counts. They said, can we predict what's going to happen in the following year? And they did a pretty good job. And that worked until it didn't, basically. Then there was a few years after that, where Google, based on the same algorithm using updated data, using new techniques, predicted that the flu trend or the flu outbreak would be roughly twice as bad as it actually turned out to be, right? And this, is in some sense an isolated, maybe an overestimation, maybe an overshoot, but it does, I think, point out that even with very good data and even with a lot of really good ideas, machine learning by itself is not going to solve every problem in the world. And I think that's, at the very least, a useful caveat to keep in mind as you're sort of considering what kind of tools you might want to use. There's a more recent JAMA editorial that I think was at least a little bit more balanced in the way it sort of thinks about machine learning and data science in the context of clinical research. So this is Big Data and Machine Learning in Healthcare. This is from just not too long ago, April 3rd, 2018. And so I think this actually did quite a good job. What they sort of think of is machine learning and big data often has this sort of air of mysteriousness, that there is some idea out there that if you have enough data and if you have the right algorithm, you can throw your data at that algorithm and it's going to solve everything. And really these exist somewhere on a spectrum from traditional statistical approaches, sort of a couple of times removed, but they're not quite as mysterious and they're not quite as opaque as people make them out to be. And they also acknowledge some of the difficulties that come from the more advanced algorithms, things like if you want an algorithm to do something useful for you, often you have to have truly big data. If you want to sort of use an algorithm to improve upon tumor diagnosis or prognosis based on some medical image, it can take hundreds of thousands of well-annotated data sets or well-annotated images before you are able to trust an algorithm to even approach what a standard researcher would be able to do after a couple of hours of training, right? So this is I think, helpful because it tries to place some of these machine learning techniques in this context of a spectrum of tools that might be available to you. And they sort of come up with this figure, which I'm not going to go through all of the details of it, but I sort of like because it says somewhere on this spectrum you've got people on this axis, and as you get more complicated algorithms, the human involvement becomes less, but the machine involvement becomes greater. And at the sort of lowest level of this, there's no machine involvement at all, and you're sort of looking at clinical experience. What does one person learn when they see somewhere between 1 and a few thousand patients? And that doesn't involve machinery at all, but it is somewhere on this learning spectrum, and that's a helpful thing to do. And as you get more complicated, sample sizes generally increase, and you end up with things like random forests, convolutional neural networks, adversarial networks, all kinds of different things that require much less human involvement, but that typically require more data to achieve reasonable results, right? So I think what I'm going to do next is talk about a specific kind of statistical learning technique with the hopes that it is illustrative of what goes on in this field in general. So what I'm going to be targeting with this example is somewhere between regression and random forests. So I would say like Lasso regression, the thing that we're going to talk about now, is somewhere right about here. People familiar with Lasso? Anybody ever heard of Lasso? Fantastic, right? So that's phenomenal. So what I want to talk about is Lasso regression. And Lasso is something that I would say is established enough among statisticians that your clinical collaborators ought to have a pretty good idea about what this is, what the strengths and weaknesses are, how to implement it, what it does, and so on. And where I want to start is with regression. Regression models in general are interested in a conditional distribution of an outcome given some predictors. If I tell you this person responded to this collection of covariates or this treatment, and this is their age and height and weight and BMI and all of these other things, you can build a regression model. And either that's going to be like a linear regression, or maybe you have a binary outcome, you're going to have a logistic regression, whatever. You've got some expected value, some response for your subject based on all of their variables, and you want to sort of learn from these things, right? And you can have more than one of these. You could have a beta 2 x2 up to beta 3 x3. You can tack on a bunch of covariates and confounders and see everything that's going on. People are mostly familiar with this sort of standard regression setting, yeah? Familiar enough? Fantastic. So why people like regression is because there's a lot of things that are great about regression. It is a well-understood traditional statistical approach, meaning that if you sort of fit one of these regression models, you can interpret the coefficient as the expected change in y for a 1-unit change in x, or you get an odds ratio, or you get whatever, right? You have some understanding of what that model does and where it's coming from. The coefficients are interpretable, and you can also do inference on these things. So you could, for example, test whether or not a treatment has some effect in the average outcome of the treated group compared to the untreated group, right? All of this is sort of standard regression kinds of things. The problem is a lack of scalability. What I mean by a lack of scalability is that we now exist in a context where instead of a couple of dozen covariates and maybe a treatment that you're interested in, you might have thousands of covariates. You might have genetic information measured at hundreds of thousands or hundreds of thousands of locations along a genome, and you still only have like 100 people, right? If you tried to fit a regression model in that setting, you would have real serious problems. It's for a variety of reasons, just going to sort of break down completely. And that's where regression fails to scale well, right? So if you have some covariates, you can do some model building procedure, whatever you want to do. If you have a lot of covariates, there's not a ton of things you can do. And that is exactly the goal of regression, is the goal of this Lasso approach, is to try to deal with a setting where you want to fit a regression, but you have more predictors than you can actually put into your model, and you need some way forward. You need some idea about what exactly is going to happen. So this is the most math I'm going to put up, but I think it is helpful to talk through what's going on, just to give a sense of like, first, what we're doing is not so different from regression at all, but the way that things are different does matter, right? So if you were going to go and fit your usual linear regression model, your main goal is going to be to minimize a residual sum of squares, right? You say, what is the expected value for this subject based on these predictors, and let me pick the covariates, let me pick the coefficients, sorry, that does the best job of fitting these subjects. You're going to minimize a residual sum of squares, right? And that's basically what you do. It's a little bit different if you're doing like a logistic regression. That's not a residual sum of squares. But the idea is to say, given these outcomes and these covariate values, what is the collection of coefficients that does the best job, right? Now that minimizing the residual sum of squares shows up when you're doing Lasso as well, but Lasso adds this new thing right off to the side, meaning what you want to do is not just minimize the residual sum of squares, but minimize what's called a penalty. And what this penalty does is it takes beta 1 plus beta 2 plus beta 3 plus everything that exists in your model, and it just adds up all of your coefficients. Right? So if you have really big coefficients, if all of your covariates have large coefficient values, then this thing is pretty big. And it might be that those are the things that make your residual sum of squares small, but now you've got a penalty on here that's saying you have to pay a price for having large covariates, or sorry, large coefficient values, right? And so this Lasso problem says, how do we minimize goodness of fit, how well our coefficients do at explaining our data, with some very explicit term that says you have to pay a price for putting things in your model in the first place, right? And the way you sort of strike this balance is through what's called a tuning parameter lambda, which I'll talk about in a couple of minutes. But the idea here is to say, if I wanted to get as good a fit as possible, I can set lambda equal to 0 and only worry about the residual sum of squares. And if I don't care about fit at all, I can set lambda equal to infinity and say, let's make all of these things equal to 0, because that's how I'm going to minimize my penalty, right? So you're choosing basically between those options, best fit you can come up with, and everything equal to 0. And the goal is to find something in between those two things, something that balances goodness of fit with everything being 0, okay? All right, and like I say, this is the same basic idea, whether you're doing like a linear regression or logistic or Poisson or whatever you want to do, okay? So how does this work in general? Well, like I say, this is the same equation as the last slide. I'm just sort of keeping it up in case I need to point to it. What happens is if you sort of choose a lambda value that's just right, a lot of your coefficients are going to be set exactly equal to 0, and the stuff that's important is going to be kept in your model. And so in this sense, if you have 100 or 1,000 predictors and not that much data, what you're able to do is trust Lasso to go through and set a lot of coefficients equal to 0, and all you're left with are the few things that should, in some sense, be in your model. What you're left with is just the stuff that should be important, and this has saved you the step of doing that model building procedure. You don't have to go through and check everything one at a time. You're just sort of focusing in, you're trying to get the best result that you can, all in one shot using this Lasso penalization. So that's why it gets referred to as automatic variable selection, meaning you've got a bunch of variables, you're selecting the ones that are going in your model, and it's automated in some sense using this tuning parameter selection, okay? Now the end result of this is going to look like a regression model in the sense that you'll have your y equal to beta 0 or b0 plus b1 x1 plus b28 x28 plus b100 x100, and then nothing else in there. So it looks an awful lot like regression. And what you get out of this are predicted values, meaning if I give you some new covariates, you can tell me what the expected response for a new subject is going to be, okay? But there are a lot of drawbacks that go along with this, right? So in particular, you can't really get p-values out of Lasso. It's just not going to give you something that says this is statistically significant at the 0.05 level. It's not what it's designed to do, right? The interpretation is tricky because it looks like a regression model, but everything's been sort of penalized, and so the exact interpretation that you might want to use doesn't really hold, at least in the ways that you would want it to. And there is still, while we have avoided this idea about having to do model selection, you do still have to choose that tuning parameter, which is a problem in and of itself. And then if you were to ask the question, Lasso returned these 3 predictors, what would happen if I just built a model using those 3 predictors? You would get different coefficient values, right? So it's not sort of picking the things out exactly as they would appear in a usual regression model. It's doing some other sort of funny business behind the scenes, okay? Okay, and like I say, I think Lasso is a useful place to start because it's sort of one step past regression, but the kinds of drawbacks that I'm talking about, the lack of sort of very concrete inference, the difficulty of interpretation, the need to choose tuning parameters in some way, that is consistent across a wide range of statistical learning approaches. Yeah?
Could you speak just in a little more detail about the last point? I didn't quite understand.
Yeah.
The coefficients for included covariance are not the same as in regression.
Right, so that's a good question. What do I mean about this last point? So if I set out and I did a regression, and let's say I've got 100 predictors, and I went and built a regression model that said y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus some error term on top of that, right? And I'm fitting this using usual regression kind of approaches, okay? And then I said, let's take every predictor that I have and throw it into a Lasso regression model. And I'm just going to assume that it also picks out x1, x2, and x3, right? So this is, let's say, regression. And just to spice things up a little bit, I'm going to change colors if I can. If I can. So then let's say we fit a similar sort of a thing with Lasso, and we got, let's call it B0 plus B1 x1, B2 x2, and B3 x3. And like I say, this is Lasso. And the question, what you might hope is that B0 and B1, or sorry, B1 and beta 1, B2 and beta 2, and B3 and beta 3, that those will be the same, right? That what Lasso has done has picked out the variables that are important and assigned them exactly the thing that I would get if I had just fit a regression using those things. And the truth is that these are not equal to each other, right? None of those things are going to be the same. Because of the tuning parameter and the penalty, right? So what's happening, and I'll show a slide of this in just a second, but what's happening is as you change that penalty, that tuning parameter value, the penalty applies to everything, right? So what it sort of does in general is it starts bringing all of your coefficients down, it shrinks everything a little bit, and eventually those things go all the way to 0 and they drop out, but the other stuff is still being sort of pulled in at the same time. Yeah. So that's why I say the interpretation of this is going to be different, right? It's not that you can't really interpret B1 and B2, it's that you probably shouldn't interpret it in the same way that you would a regression coefficient because it's been pulled in substantially by the fact that you're doing this penalization. Good.
Sorry.
Yeah.
Just one quick follow-up. So would anyone ever take the results from Lasso if you had 50 covariates and Lasso reduced all but 6 of them to 0?
Mm-hmm.
Would anyone ever take the other 6 predictors and put them in a linear regression model?
People would. I don't recommend it, right? And like I think that's an important point is that it will seem like Lasso is doing exactly what you want it to. It will seem like it's sort of pulling out all of the different covariates that you're interested in, but the way it's doing it is focused in such a different way that you probably shouldn't try to make the two approaches compatible. Yeah? Okay. So I do want to talk just briefly about this tuning parameter selection because I think, again, it's not so much how exactly you do tuning parameter selection that's important, it's how this relates to the emphasis of some of these statistical learning approaches in general, right? So if what you have to do is balance your residual sum of squares and your penalty, what you got to do is figure out what value of lambda you want to pick, right? And the way this generally happens is the following. You probably can't talk about inference, you probably can't talk about some other things. What you can talk about with Lasso is prediction accuracy, meaning if I give you some new collection of subjects, you can make predictions about the outcomes for each of those different people. And so what you probably want to do is go through and choose this tuning parameter to optimize that criterion, to give you the best predictions that are possible. Again, this has nothing to do with statistical inference. This is all focused on prediction. Do I get the best guess for a new subject? And the way that this happens in practice is using cross-validation. So it's pretty rare that what you have is just like an extra collection of subjects hanging around so that you can use their data. So what happens in practice is you take your full data set here and you chop off some random subset of it, and you take these people off to the side. These are your testing subjects. And then you take these people as your training subjects. and you fit Lasso using your training subjects with lambda, the first value, and you see what kind of predictions you got. And you do it with your second lambda, and you see what kind of predictions you got. You get it with your third, and you see what kind of predictions you got. And you just try a bunch of different lambda values until you get the one that gives you the best predictions, right? And so the reason that I think this is instructive is that is, in broad strokes, what a lot of statistical learning approaches endeavor to do, is not to identify statistically significant or biologically plausible or whatever. It is not focused on causal inference or on mechanisms underlying a disease process. What it's going to give you is the collection of things that give you the best predictions, right? And that, again, is part of the reason that interpretations are difficult in these settings, is that it's not clear that what ends up in your model is biologically meaningful or important for whatever disease you have. It's just the stuff that gives you the best predictions. Now, often those things do overlap, and so that's one reason that I think Lasso is a useful tool. But keeping in mind that what these statistical learning approaches are optimizing is your ability to make a prediction about some future subject is an important reminder of why you shouldn't sort of worry so much about inference, or you shouldn't worry so much about interpretation. Good. Yeah.
Can you give us an example of like cases in which Lasso has been used that have given some
Yep.
information?
So, yes. So what I think moving on to next is a more concrete example. And I think this is, the example that I'm going to use, I'm pulling out of publicly available data rather than like a data set that I've analyzed myself. And part of the reason that I wanted to use publicly available data is, one, sort of to be consistent with this idea of reproducibility, and also so that if you want to play around with this yourself, you're free to do so. I can make available like a report similar to the one I had shown previously that does this analysis. So what this data set, and this is like a quintessential data set in a lot of these statistical learning software approaches, takes 72 leukemia patients, 47 are ALL and 25 are AML, and you have 3,571 genes, right, that might be predictive of leukemia type. This is a setting where standard regression is not going to do you an awful lot of good. You don't know which of those genes you want to put in, and if you tried to fit a model using all of them, it would fail spectacularly. So you have to do something else. And this is one of the settings where people sort of like to use Lasso. It's one of the earliest examples of using Lasso, at least to the best of my knowledge. It's been used, I would say Lasso and related techniques have been used sort of broadly in this kind of problem. If you're using sort of genomic information, it's been used to some extent in neuroimaging or other areas where you have high dimensional predictors and not a ton of subjects. But this is the kind of setting where things come up, right? And so what sort of happens when you do a Lasso analysis? And like I say, I can sort of pull up, I think, the software, the code that goes along with this. There's some stuff in here that's maybe worth talking about and maybe not. So what you end up with when you do this kind of an analysis is the following, right? So what I've done here is tried a huge range of lambda values. These are on the log scale. Got a big old range of lambda values, and what I have said was, for this lambda value, let me fit a Lasso logistic regression, and it omits 3,550 of the 3,571 predictors. You're left with about 20 things that seem to be important in your model. All the rest of them, even by this lambda value, have been shrunk entirely to zero. And then what I do is I sort of move along here, I increase lambda, and what happens is, in the balance of power in this sort of optimization thing, goodness of fit is starting to fall out of favor compared to the penalty that you have. And you start seeing a lot of these coefficients are being shrunk down towards zero. And as I increase this more and more things get shrunk down towards zero. This value is the optimal based on cross-validation. And so what has happened here is that in this logistic regression framework, I started out with 72 patients and 3,500 genes, and Lasso says, if you want to make a prediction about what leukemia type a person has, these are the 5 genes you need to care about, and these are the coefficients that give you the best prediction, right? Again, there's no sort of p-value that says with some statistical significance, these are the best genes. There's a lot of stuff that you wouldn't want to say based on this, but you can say, strictly in terms of prediction, that this is the best you're going to be able to do. Okay? Yeah?
Are the lines representing different genes?
Oh, yeah, sorry. This say B1, this is, say, B2, and B3. These are coefficients in a logistic regression model corresponding to individual genes, right? So this is, if you had the sort of gene 1 and gene 2 and gene 3, you could sort of stack these up to get your logistic regression model. And what's happening is these things get shrunk down. Many of them go all the way to 0 as you increase this tuning parameter. Okay. Other questions? All right, so like I say, part of the reason that I like Lasso is because it is close enough to regression to be sort of just another step farther while still giving a lot of the useful intuition about what statistical learning approaches do, how they work, and the kinds of interpretations that you might be able to get from them. Yeah.
So when you say optimal, how is that measured?
How is that measured? Yeah, so I think in this case, I would have to go back and double check, but basically what they're measuring is a misclassification rate. So what you would look at is, based on the predictors that I have, would I classify this person as more likely to be AML or more likely to be ALL? And then based on how you do that classification, it's saying which one does the best. Yeah, it's broadly similar to looking at like an area under the curve or like a sensitivity or specificity. You're choosing some criterion to evaluate prediction accuracy. Yeah. Yeah. Good question. Thank you. All right, so the last thing that I want to mention, just because I think this is a useful thing to keep in mind, is that there is again this sort of general sense that if you have enough data, you can throw a machine learning algorithm at it, or vice versa, and everything will get fixed. And that's not usually the way things work out. Meaning that the best statistical techniques aren't going to fit what is underlying, what is fundamentally sort of a bad data. So in the context of how you might think about doing a clinical experiment, you sort of think about what it is you care about measuring and who it is you might measure this on. And there are a lot of steps before you get down to the data that you're going to use. And this sort of survey statistic at the very end of thing could come from a t-test, and it could come from Lasso, and it could come from a deep neural net. But if the measurement that you have isn't actually valid for the thing that you care about, and if you have measurement error and non-response and data processing errors on the one side, and at the same time you're sort of not sampling from the population that you care about, the best statistical learning approaches, the best statistical approaches can't solve that problem. And that's part of the reason that the embedding of data science into a context matters so much, is that understanding what all of these steps are before you can determine what method to use is a critical thing to get right. And so this is, the flip side to that is that you don't just get a free pass to say, like, no, nothing's ever going to be good enough. There's a lot of useful data sets out there, and even imperfect data can be used for something. You just have to evaluate not just the method that is being used, but the overall construct that led to that being even a question that was asked in the first place. And I'll sort of close with this quote from the more recent JAMA editorial. It says, even if we're reluctant to repeat the cliche, even the best machine learning algorithms, garbage in, garbage out remains true. If you have bad data and you don't worry about that, then what you're going to end up with is not going to be particularly informative or useful. I'll point out there are a couple of data science resources. I know there's going to be a Bird R short course. The class that I have on data science, sort of a semester length, mostly focuses on things like coding and reproducibility and less on statistical learning. All of those materials are available online, and thank you very much.